good. Other than apparently everybody keeps going to Kensington 1 up here.
This is Kensington 1.
Sorry, we're going to Kensington 2. Because it's the big thing that says Kensington Suite.
Great.
So I actually went down like,
grab some people.
yeah, actually went all the way down, made up a sign saying,
oh, awesome.
Technology deep dives, you are in the wrong place.
Okay, I don't want the on-site tool. I actually
you need the real tool.
I need the real tool.
How are you this morning, sir?
I mean, like, I've slept better. I've slept worse. I get like this thing where I see this set of people and they get jet lag, regardless of what like the actual time zone is. It's just this is jet lag. I gotta read the warning label when I come up.
Good morning, sir.
Full client video.
Yes.
Are you going to the slide flipping? Or?
Slide flipping.
I guess there's basically no reason for me to be sitting here.
Why do I have to? There's like a reload step that you have to do, right?
Yeah, moving here.
No slides available. How do I reload slides?
There should be that refresh button up there. I saw them
They're
before.
on the. They're in the data tracker. Ah, here we go. Awesome.
I checked this morning and I was like, where the hell are the slides? Oh, it's too early there, sure. Yeah, no. What are you trying to do? Presenting? Here we go, I can share preloaded slides.
Oh, yeah, there it is.
Yeah.
Oh, you're doing it?
You can, either one, you can do it.
I'll do it. All the slots you have to dismiss.
Dismiss, yeah.
Otherwise it won't. Woo. Yes. John is here, so we can start.
Telling everyone that they're in the wrong place.
Johnny, you can come on up.
Hello all, we're about to get started. Hopefully people on the remote can hear this. If someone remote can acknowledge, that would be awesome. Yay! There we go. Hopefully it's better now. Cool. So, if you are sitting in a room called Kensington and you do not see people, probably you're in Kensington 2 or Kensington 3, which is very confusing because when you first come up the stairs, you see Kensington and you walk in and it's not here. So if there are not a bunch of people in the room with you, you're probably in the wrong place. Get up, walk down the passageway with all the glass, and then turn left. Alrighty, so hi, welcome to the Technology Deep Dives on QUIC. I'm Warren.
I'm Brian.
And let's get to the next slide. This is the IETF Note Well. We're the first sort of like official session, so it's entirely possible you have not seen this. You should probably read this and figure out what all it means and talk to legal, etc. if you don't know what it means. But yep, this is our IETF Note Well. And thank you everyone for showing up so early. I realize it is ridiculously early. And also hello to everyone who is remote and here. And also hello to everybody who's going to be watching this later on YouTube probably, or some remote thing. Video streaming service of your choice. Alrighty, and with that done, let me hand it over to Brian.
So I've actually had this question in the hallway a lot. So do I have to come to the technical deep dive on Monday and on Tuesday? Well, that's really early both days. It's even earlier on Tuesday, actually, at 7:30 tomorrow. And, you know, I was asked, okay, that's a joke, right? No, I mean, it might be a joke, but it's also the truth. The agenda is split into sort of like two parts. Today is basically the basics of QUIC, right? Gets you from, I have no idea what's going on here, or I've heard of QUIC, or, you know, isn't that just the web over UDP, to having a basic technical understanding of what's going on in QUIC. Jana will be talking about the, you know, the basic introduction, a talk called The Future with QUIC. And Martin will follow up on that with a talk about how QUIC is layered and how that layering is a bit different from, you know, the intuition that you'll have from, you know, TCP over IP, et cetera, et cetera. Tomorrow, we will go a bit deeper into a few topics. So this is really about, okay, now we have the basic fundamentals of QUIC. Let's talk about how that gets deployed at scale, how it is sort of like used in the internet now, and things that we've learned from running it at scale. So that'll be Ian, morning Ian, and Lucas, who I haven't seen yet, but he'll be here tomorrow. Talking first about the deployments at scale and some of the things that we've learned through that, and then like how to observe and debug applications on QUIC. And with the rest of the time tomorrow, we will have a panel discussion with all of the speakers. So if you have like interesting questions, please hold them till tomorrow. Come at, you know, 8:30 is when that should start. And we'll have a panel up here with people to answer your questions and have some discussion about QUIC. So with that, I will stop talking and invite up Jana Iyengar, who will talk about the future with QUIC as soon as I bounce the slide share.
Thank you, Brian. Do I have to stand in the spot? I think I do. No?
I don't.
We'll see if the camera follows me. Well, thank you. Thank you, everybody, for being here early this morning. Hopefully this talk will wake you up. If it doesn't, I'll ask Martin to wake you up. But anyways, let's get started with this thing. Are we doing question and answer? Are we doing Q&A alongside? What are we doing with Q&A?
Q&A will be tomorrow.
Will be tomorrow. So if you have any questions, write them down. You'll forget them through the day and ask us tomorrow, or catch us in the corridors. So I'm going to start with just this brief agenda. It's basically, what is QUIC? And this is for, and then I'm going to talk about QUIC's immediate value proposition. And I'm going to talk about really what does QUIC enable. Next slide. So the subtext here is that the first piece is simply a short primer, a very, very short primer on QUIC. I can't do more than that. And we want to talk about how did we get the world interested in this? Like, what did we do to make the world interested in this particular technology? And finally, what was the real goal? What was the thing that we were really wanting to do? What did we set out to do from the get-go? Next slide. So before I get going on to QUIC, who am I? I am Jana Iyengar. I'm VP of Infrastructure and Network Services at Fastly. I'm an editor of the IETF QUIC specifications. I'm a chair of the ICCRG, IRTF's ICCRG research group. And I've worked on transport for way longer than I care to remember, and on QUIC also for way longer than I care to remember. But that's me. Next. And now on to a short primer on QUIC. Next slide. I'm going to tell you this. This is going to be a very short primer. There's not going to be, I don't have a lot of slides here talking about the details of the protocol, the details of the bits. We've done, I and others have done talks on these in various places. So if you go on YouTube and do a search, you'll find a bunch of these things. So my goal here is not to go into the details of this, but to give you a base from where you can dig in and get deeper. But I'm just going to start off by saying QUIC is a new transport protocol. Now, if you look at this picture, this sort of has a depiction, and Martin's going to come and thrash this picture and say, well, that's not quite how this works later. So that's fun for later. But this is roughly a schematic understanding of where QUIC sits in sort of the protocol stack, so to speak. We have the TCP, TLS, and HTTP protocols in the traditional stack. And where QUIC sits is basically parallel to TCP and TLS and some of HTTP. So yes, it's weird, but that was kind of it's not weird, it was just a compression of multiple layers, so to speak. And TLS sits sort of within QUIC, but it's not within QUIC. However, it sort of does sit within QUIC in depending on how exactly you look at it. But that's sort of the layering picture here. It is deliberately compresses multiple layers, and it deliberately sits at these in these spaces, because the goal here was to accelerate and deploy something that we could for the web. Next. So what are these features of QUIC that really made it viable and useful for the web? Well, first, it's multi-streamed. Multi-streaming is a very powerful feature. It's a very powerful service. The idea here is that you get within one end-to-end connection, you get multiple ordered byte streams. Now, this is not just multiple ordered byte streams, it's a more general abstraction. Now, this works really well for the web because the web has, every website has a lot of objects. They're all multiple, effectively parallel independent objects and so on. But this is a more general abstraction. Streams are designed to be lightweight. They're designed to be built and toned down rapidly, efficiently. And if your implementation does it right, you can use this as even a message abstraction. So you can think about this as a protocol that gives you a message abstraction in the form of streams. And for the transport nerds among you, you can build partial ordering on top of this thing. Or you can build complete ordering inside this thing. So you have those degrees of freedom with multi-streaming. Next slide. Why is this on top of UDP? It's a question that people often ask. We built this on top of UDP because UDP is what works on the internet today. If you want to build something new and deploy it, that's the way to do it. And that's what we did. Now, this doesn't necessarily mean that the protocol has to live in user space. However, remember that if you wanted to build something on top of IP, you are necessarily stuck to being inside the kernel. And that is a big problem for us also in terms of building, deploying, shipping things. So being on top of UDP gave us two significant benefits. One of them was that we could get through the internet as it is with middle boxes and firewalls and everything else. And it allowed us to deploy in user space. So those were two significant benefits, which is why we use them. However, it requires us to recreate a bunch of TCP functions on top of it. So we had to redo all the TCP functions on top of this, but we didn't simply redo them. We did a better job of doing them. Because we've learned from the past. We wanted to incorporate all of the learnings of TCP, and we did. And importantly, QUIC has encryption baked in. This means data, everything that is carried by the QUIC protocol and QUIC headers are all protected. And this uses TLS 1.3 for key negotiation. And this is basically a really important premise. And I'll come back to this in a moment. And again, Martin's going to go into more detail on exactly how this is done in QUIC. But this was really important to us. Why was this important to us? Well, of course, it was important to us to protect the metadata. We know today that if you were to design a protocol that was not fundamentally protected, that seems like we're not learning the lessons of the past 20 years. So we did that. But there was an even more important lesson here, or an even more important reason for doing this. Middle boxes ossify protocols that are exposed. We did not want QUIC to be ossified. TCP is today ossified. Many other protocols that have been deployed in the wild in plain text are completely ossified. You cannot change them on the wire without seeing unexpected, weird interactions with middle boxes that have ossified them or have certain expect certain behaviors of them. Oh, that's the next room. So sorry, go back one slide. So with baking and encryption, what we were able to do is basically say that only the endpoints can really understand and change the metadata, the headers in the protocol, as well as the body. And that's an important thing, because now middle boxes are unable to change the headers or to obfuscate or to mess with the headers or even read the headers. So they can't have any expected behaviors, which means that endpoints are free to change the protocol as they see fit. What this means is that QUIC becomes evolvable. So when QUIC gets deployed, it becomes evolvable. That was our goal, and that's why encryption is baked into QUIC. Next slide. So that is my rough introduction into QUIC. And I'm sorry if you didn't see all the header bits that you wanted to see, and I don't want to do that here to you early in the morning on Monday. You're going to see plenty of, if you want header bits, walk into any room this week. You'll see plenty of those. I'm going to talk to you about what QUIC's immediate value proposition was. How did we get the world in? So these are the features, right? This is what I talked about. This is how we talk about QUIC. How did the world get interested in QUIC? So QUIC broke new ground in several ways. The first thing was the zero RTD transport and crypto handshake. Again, you're going to hear more about that after my talk. And this is fundamentally difficult to do with TCP and the split TCP TLS models. You've got TLS sitting on top of TCP. They end up having different scopes. When I say different scopes, I mean scopes of identity, scopes in terms of where the connection gets terminated in the network, and that makes it fundamentally difficult to do something like zero RTD. People have argued, people would say, you know, isn't it the same, isn't zero RTD in QUIC? So before I talk about the same as TCP, what zero RTD and crypto handshake, what that gives you is a low latency connection setup. For those of you who've not been paying attention, zero RTD means zero round trip time delay before data is exchanged on a connection. Excuse me. So we've created a zero RTD transport and crypto handshake. Now, TCP could do this with TCP fast open in TCP and with TLS 1.3 and zero RTD in TLS. However, because of the split model, you still end up having different scopes. You have TCP that doesn't understand domains, certs, things like that. It understands only IP addresses. TLS operates in a different space. And you have a split between an understanding of what the endpoint identity itself is at these two levels. You can reconcile these things, but there's a lot of nuanced work to be done there if you want to make this work in the split TCP model. Next slide. Connection migration was another thing that we wanted for 20-25 years to build into transport technologies, and we finally got it in, and we were able to build this into QUIC. Again, this is fundamentally different to do with TCP and the split TLS TCP model. In part because of the endpoint identities, but also in part because TCP, we've done this with MPTCP. IETF has done this with MPTCP. But I would again challenge you to think about what we should think of as our end goals. We want this to get deployed everywhere. With MPTCP, you still have to play nice with the operators, with the network devices, and so on. I don't mean that we shouldn't play nice with the operators. What I mean is that we can't wait for every operator and every middle box vendor to come on board before we consider a protocol deployed. That is a very, very long pole, and that makes the tent unlivable in. It's too long a pole. So that's basically connection migration. Again, we've deployed it. It's being used already. Next slide. And we are able to build troubleshooting and debugging capabilities. You're going to hear about this a little bit more from Lucas tomorrow. But the difference here is this. The value prop here is this, right? So with anybody here who's done debugging, kernel debugging? Anybody? Okay, a fair number of hands. Excellent. Have you also done application debugging? Have you tried to correlate those traces? That is a pain, right? So when you have certain application behavior and you go, okay, I've got application traces, and you go, okay, now I need to grab the TCP traces or S trace or whatever it is that you need to do. And you need to go down to the kernel and go all the way down the network path to figure out everything. You are trying to use completely different pipelines built by completely different people for completely different use cases and try to correlate them. Companies that have managed to successfully build those things have used them very, very effectively. However, it's not a small order. It's difficult, right? So being in user space for QUIC basically gives you the ability to log transport network level traces alongside application level traces. That is huge because you don't have to go around doing this separately. You can log alongside the application traces. You can log things like what is the congestion window value, what is the state of the connection, what happened when was streams created. Again, you'll hear more about this from Lucas tomorrow, who'll talk to you about logging under the logging format that we're standardizing for QUIC here. But we get much significantly richer capabilities for doing this in user space. Next. So actually, go back one. I think may have missed. Oh, right. I meant to say this here. There is a another really cool thing which I'll show at the end of today. If we have time, I'll demo it. But one thing that you have a problem with, for instance, is if you have poor behavior at the client side, for instance, you can grab client side packet traces, or you can report it to the server side, whomever is at the server, and you can say, hey, go dig into this particular trace. I'll give you an identifier for a connection, for instance. Go find out what happened with that connection. Why was it behaving poorly? You have no other recourse. And on the server side, what we would do at the server side is generally we end up having to find your connection. Now that is an impossibility. Usually finding a connection in the fleet of servers that we have and so on is super difficult to do. And it's and then go trace it, track it, find where the client is connected. It's really difficult to do. What we were able to, wouldn't it be cool if the client could basically ask the server and say, hey, can you just send me your view of our connection over the connection that we have right now? Like your packet trace for my connection, just send it to me over the same connection that we already have. That is what we built. And we were able to do that. Next slide. I'm not going to show you this demo right now because it's a bit tricky to get going. But the links are here. Go to the video only link and then go to the self-trace link using the same browser window, meaning that you'll have a connection going over you'll have a stream going over the same connection. And that only works, of course, if you're using QUIC. And I'm happy to show it to you later if I can get it going. So this is really, really valuable. At the client, you're able to see a server's packet trace. Now, I'm going to move to the next thing, which is transforming server architecture. So I won't go into the details of this, but direct server return is an ability for a server to be able to hand off a request to another server and have that server serve the user directly. So it's sort of like if a client requests a resource from a server, the server doesn't have the resource, but knows another server that has it, is able to sort of kick the connection over or the request over and have the response served directly from there. This is called direct server return. It's called direct server return because normally what commonly happens, and the easier way to solve this problem of I don't have the content, somebody else does, is client connection to the server, server connects to the other server, receives the content, serves it back. So there's a full path back. Instead, you bypass this intermediating server on the return path. That's called direct server return. We are able to design this in QUIC, and some of us have been building this into our server infrastructures. And the reason we're able to do this is because in QUIC, again, in terms of how we build the transport protocol itself, we were able to separate the sender's view from the receiver's view of the world. And in this particular case, that plays very nicely, allows us to actually build something like direct server return. We can have multiple servers sending with one receiver receiving. This is again fundamentally difficult to do in TCP. Next slide. So this is how we got the world interested. These are the different things. These are the different benefits that we brought out, and and this is how all of us got excited about QUIC and so on. But I'm going to now talk about what QUIC is enabling. Right. Next slide. What does QUIC enable? So QUIC enables multiple new technologies that you can build within QUIC. So you can hear about, you won't hear these experiments today, but maybe tomorrow. There are new congestion controllers that you can easily build and deploy. I know that Meta's done this, Google's done this, Fastly, we've done this. So it makes it much easier to deploy these things in QUIC than it has been in TCP. Next slide. If you've not heard about MASC, MASC basically employs HTTP3 and QUIC to create hidden tunnels, right? And this is something that you can, again, QUIC is enabling this technology. Was it possible before? Yes, but this makes it much more efficient, more performant, and also more efficient at the server stacks to be able to deploy something like tunneling. And this is not just, I'm not just talking about things here that could be built. This has been built. If you've heard of Apple's private relay, iCloud private relay, that basically uses MASC extensively, and it carries a ton of bytes today. If you have an iPhone and you turn it on, you're using MASC, you're using HTTP3 and QUIC to do this today. Next slide. And finally, media over QUIC, or what I call the new world for WebRTC refugees. Is a proposal to do media directly over QUIC. And that's, again, QUIC is enabling these technologies now to happen because it's feature rich enough that you can actually think about doing more interesting things directly with the transport. Next slide. But I'm gonna offer that the real value of QUIC was something else. Next. So QUIC, I've told you that the QUIC makes the web faster, more resilient, more responsive, but this is just the beginning. Next slide. QUIC enables these technologies I talked about. So it becomes a platform for these new technologies, MOQ, MOC, MASC, other stuff that we want to deploy. Next. And I've also told you that QUIC is a transport technology that can be evolved on the internet. Because we manage to encrypt everything, we can evolve this thing going forward. It is already continuously evolving, and multiple versions of QUIC already exist in parallel on the internet today. And next slide. I'm going to offer that we've pulled a sleight of hand. We basically convinced everybody that these are the reasons we wanted to deploy this thing. HTTP was the reason, and getting these milliseconds of latency improvement and these features were the reasons. But next, we used HTTP and the web as a vehicle to deploy QUIC into almost all server and client deployments. QUIC is deployed now widely. Almost every server deployment has QUIC in it. Almost every client browser and other client libraries, they all have QUIC in them now. Next. But our goal really was to create an end-to-end transport that allowed for end-to-end transports and technologies to thrive through an ossified internet. And I would say that we are sort of somewhere, not at the beginning of this journey. We managed to get somewhere. Hopefully we'll get to the end of the journey, but we are certainly much farther along than I thought we would get to. So thank you.
Thank you very much, Jana. Next up, we have Martin, who will be showing us some header diagrams, I think.
There's no header diagrams in this slide. Supposed to be. All right. So DEX coming. All right. So I'm going to talk a little bit about the QUIC handshake and in particular some of the security properties. Security being one of the sort of primary drivers behind building this thing. Do you have a clicker?
Yes, but it doesn't work.
It doesn't work.
Oh, lovely.
We have a non.
All right, well,
clicker.
next slide then.
Clicker is to say next slide, and
Yeah.
that I catch your cues.
So there's a couple of things in here. I may not get to some of the later things in any real detail, but that layering diagram that Jana was talking about, I think we'll spend a little bit of time on that. Quite possibly the most difficult part of getting QUIC working was integrating the TLS handshake into QUIC. There is something of a tight interaction between those two pieces, and it turned out to be extraordinarily fiddly. And we were given a protocol from the work of the folks at Google who had designed their own cryptographic handshake. And it was broken in tiny, subtle, and very significant ways that required years of work to get to work. So next slide, please. So you've seen what is, I think, the standard reference point for how we think about layering in QUIC. There's this little TLS slice that's sort of jammed in on the QUIC layer, and this is something that I think makes people who like their nice layer cakes a little uncomfortable. And we'll explain why that's the case as we get through this one. Next slide, please. So at a very high level, QUIC connection setup does everything that TCP does and everything that TLS does, all sort of integrated together. And we did that for a number of reasons. I think the primary one being performance. So what we wanted to do was avoid replicating a lot of the security work. It turns out that building a good security handshake is extraordinarily difficult, and TLS 1.3 is the result of a number of years of work. And we didn't want to have to redo all of that work because we're also building all of the TCP bits entirely on top of UDP, which is an entirely new protocol, and that's more than enough work. And it turned out to be even more work than we anticipated when we came into this. So the way to think of this is that TLS provides all of the cryptographic assurances that you might expect from a protocol, and QUIC provides all the things that TCP would provide, being reliable ordered delivery. And in turn, they each provide services to the other. TLS requires ordered reliable delivery. QUIC requires a secure handshake. Next, please. So we're taking the core TLS guarantees, authentication, confidentiality, integrity, and all of the core TCP guarantees at the handshake level. Now, other people can talk about streams and the various application semantics that we're providing QUIC, which include some of the core TCP guarantees, like in order, reliable delivery. But for the handshake, there's a lot of the things around the TCP handshake that I think weren't in the original versions of TCP, but ultimately TCP needed to have, which are things like being assured that the other side that you're talking to is willing to talk to you, for instance. And that turns out to be an extraordinarily important part of the design of QUIC. And we'll talk about that as much as we can. The other thing is we were looking to do better than any of these protocols. We have a new protocol that we are implementing here. We took every opportunity we could to make things better. And I'll touch on a few of those points as we go through. Next, please. So RTTs. TLS 1.3 is optimistic in the sense that a client will guess what configuration will work for a server, and that will, in the case that the guess is correct, save a round trip time. QUIC does the same thing. A typical handshake in TLS is a sort of three-way exchange. You have the client send a message, the server respond, and then the client finishes that off with a confirmation message. If the client guesses wrong, you have another round trip added to that. And one of the sort of themes that we'll have with QUIC is that it has a very short handshake if everything goes correctly, but it turns out that you can add multiple round trips. If you have packet loss, the client guesses wrong, the server is under duress and wants to tell the client to back off and wait a little while longer. And so we have this very flexible handshake ultimately. The key insight is we have sort of this multiple round trip handshake, and I say here that typical handshake is 1.5 RTT. In practice, I think the messages we exchange is 2 round trip times. But under normal circumstances, if the client guesses correctly and the server is willing to communicate with the client, we can send data from either side after that first exchange between the client and server. We're actually sending before the handshake is complete. And in the extreme case, if the client has been to that server in the past and set up the 0 round trip time thing, there is no delay for either end. The client sends immediately, application data is flowing immediately as the handshake is commenced. Same on the server end. As soon as the server sees the client's first message, it can start sending things to the client as well. And these performance guarantees were sort of central to the appeal of QUIC, and they're the core of the performance guarantees that we're providing here. Next. So this is what the TLS handshake looks like. We have some key agreement and configuration that is exchanged more or less in the clear, and then some authentication information. And you can sort of see here, we've got these lighter lines that say where the data is being exchanged. There's a flow from the client. There might be some application data following after that one. There's a flow from the server. There might be some application data. And then finally, at the end, some more messages, lots more data at that point. Next, please. That's what happens when you put TLS on top of it. And there's a little note there saying that we had to tweak TLS in order to get this to work. And that's going to be a bit of a theme as we get into this one. Next. So the QUIC handshake sort of takes the TLS handshake and builds on top of that. TLS messages have essentially 4 types of keys that are used. The no key in the case of TLS is turned into a real set of keys in QUIC. So we have what we call initial keys, which are not secure in any meaningful sense, but they provide us protection against ossification to the points that Jono was talking about before. Every single version of QUIC uses a different set of keys. If you don't know the keys, you can't speak that version of QUIC. It's sort of a nice little protection against someone who might be inclined to interfere with the handshake, but if they don't know the version of QUIC that's being spoken, they don't get to interact. TLS also provides handshake keys. Those handshake keys protect the details of the handshake. The security guarantees there are very, very interesting. Those of you who know TLS will perhaps have a better idea of what those properties are, but essentially we're providing confidentiality for things like the server certificate and a lot of the configuration parameters that the protocol has. The TLS bytes are put into specific frames within the packets. So we have packets with frames in them. The packets are protected with these keys. And we put multiple packets in the one UDP datagram, as it turns out. And QUIC, after many iterations between first going with something that was based on DTLS, because why not? DTLS does UDP, turns out to be a bad idea. We went to TLS and TLS exporters for getting keys. Ultimately, what QUIC does is runs the TLS handshake, and then when TLS produces keys, QUIC reaches in, takes those keys out and uses it for packet protection. TLS doesn't, TLS record protection isn't engaged in this. The raw bytes coming out of the handshake of TLS are used directly by QUIC. So the final 2 types of keys we have are 0 RTT keys, which the client uses to send to the server if it happens to be attempting 0 RTT, and then the final application data keys, which are used for everything once the handshake is completed. We also have a key update process that rotates those keys periodically to prevent them from wearing out. Next, please. So this is what the simplified handshake looks like. We have the client sending an initial packet, which contains a crypto frame, which contains a TLS client hello. And on the server end, we have an initial packet, and that contains a crypto frame that contains a server hello. And that is all effectively sent in the clear, although we're using these special QUIC version specific keys that are generated. The interesting thing to observe here is that there is a flow that goes from the client to the server and back again in the clear. And then in the opposite direction for handshake keys, there's a flow that goes from the server to the client and back again using those handshake keys. And then finally, there is application data flowing from that point onwards. Now, this is a quirk of TLS, but what you will actually see here is there's a final message that confirms the handshake is done at the bottom there that the server sends once it's received everything from the client. And we spent years trying to avoid putting this message in. It turns out to be absolutely crucial in a number of scenarios. We had the worst problem with handshake deadlocks and all sorts of weird corner cases before we decided, look, let's just put another message in here. What this means is ultimately this is a 2 round trip protocol. You can see 2 round trips on this diagram here, but you're sending data a lot sooner than that. And that's one of the weird things about operating this protocol. Next, please. Of course, all of this integrates with QUIC. And so QUIC, underneath all of this, is providing acknowledgements for all of the data that's being exchanged back and forth here. And so that's what you see here, is that every single message that is sent is acknowledged using packets protected by the same types of keys for various reasons that should be obvious. You can't acknowledge something with a different key because, well, maybe the other side doesn't have that key yet. And so there's this weird interlocking thing that goes on here, including some implicit acknowledgements in certain cases, which gets a little bit interesting as well. But this is to sort of illustrate that QUIC is providing all of the transport reliability features that TLS requires. TLS sends very large messages that need to be sent and received in a very particular order. Otherwise, it just doesn't work. And QUIC provides those facilities. Next, please. So this is ultimately what we have in terms of the layering diagram. And I think thinking about layering in the classic sense, where you have a protocol that sits on top of another protocol, doesn't really work for QUIC. The key thing to realize here is it's more like a software architecture diagram where there are certain components that provide different capabilities and they have interactions with other components. If you think of the TLS stack as taking handshake messages and returning handshake messages and then providing information about state changes and the various secrets that it might be generating, then you have the ability to build a component that then sits inside the greater protocol. And so you have crypto streams responsible for exchanging those handshake bytes back and forth. And then you have a packet protection layer that takes the packets that you're sending to the other side and takes the secrets from TLS and protects those packets or removes protection from those packets. And then of course, all of the things that we concretely care about in terms of streams and ultimately the QUIC datagram work as well is sort of sitting in there, providing more frames that can be exchanged back and forth. So this is what I tend to think of as the ideal structure of QUIC on the inside. And it's not that simple, but this is a gross simplification of that. Next, please. So the other part of all of this is actually mostly new in the protocol. We've taken inspiration from protocols that preceded it, TCP and other things. But the denial of service mitigations in QUIC as part of the handshake and later are somewhat more interesting than the software engineering exercise of getting a quick TLS stack crammed in. So we have a few basic rules. We had a long debate a little while ago about where this number 3 came from. And no one knows concretely. We had a number of people involved in the design of this, and none of them can remember where the number 3 comes from. But there's this basic rule that we follow in QUIC, is if you're sending to an address that you haven't confirmed is willing to receive the packets that you're sending, only send 3 times as much data to that as what you've received from that apparent address. So your random packet appears from the internet, from some arbitrary address, you can send 3 packets in response, no more. There's an address validation process that we use to say, send to that address and get confirmation that that address is live and willing to receive the packets that you're sending to it. And we have multiple types of address validation in QUIC because of the way that we design the handshake, and ultimately, I'll touch on this later, migration. And really what we want to do here is ensure that QUIC is not used as a platform for denial of service attacks against unwitting and unwilling victims on the internet. It turns out that we don't want to be memcache. And that's probably not such a pretty important ultimately for making sure that everything works properly. Next, please. So the basic handshake amplification attack is that a client sends an initial packet that happens to have 0 RTT in the same datagram. You can put a request in the same packet as your initial thing. That might be a totally valid packet that a server would accept under normal circumstances. It might be very happy to accept that packet from the client. But if the client manages to spoof the address, the return flow from the server, which contains all of the QUIC handshake information and potentially the answer to the question that they asked, could be very large. And the poor victim who genuinely owns that address might find themselves on the receiving end of a large flood of packets from a very well-connected server. We don't want this to happen. So next slide, please. So TCP solved this, I think, a long time ago. I don't know when that was, but it was before I was involved in any of this. And it has a 3-way handshake. Of course, when we're doing TLS and TCP, this adds an extra round trip to the setup, which is a little annoying. That slows things down a little bit. But essentially, TCP confirms its willingness to communicate before you start doing any of the TLS stuff. But in QUIC, we put this all together. So we're doing the cryptographic handshake and this confirmation to communicate all at once. And of course, not every QUIC server is willing to participate in all of this extra work before confirming that someone on the other end is actually willing to talk to them. So we added a retry mechanism, which is very much like the TCP, SYN, SYNAC with the cookies. The SYN cookies. Next, please. This looks approximately like this. The client sends a packet and maybe some extra packets, and the server says, hey, no, please confirm before proceeding. And it sends the client a token. And if the client's a genuine client, it will receive that token and can stick it in the packet that it generates for the next attempt, and everything moves on from there. And the server has now received confirmation that the client is able to receive the messages that the server is sending, and the client is willing to participate in the protocol. That's nice. Next, please. Retry, of course, is probably not something that you want to do because you're adding a round trip time to the connection setup. It is particularly good for cases where the server is under stress and they want to make sure that every client is genuine. If they're under attack, then it might be a good way to manage that. Or if you think that the traffic is coming from somewhere that is unreliable for various reasons, the reputation systems that you have indicate that it may be a little shonky. But that round trip is expensive. So we have some tricks for the case that the handshake is shorter. Next, please. So what we need to do is prove to the server that the client saw the server initial packet. How do we do that? It's very simple. The first exchange that happens in the clear between the client and server establishes some cryptographic keys, and it does that based on information in those packets. The next set of packets from the client, these handshake packets, use those cryptographic keys to generate new packet protection keys. If the client produces a valid handshake packet, that is because it saw everything that the server produced. And so we have what amounts to an implicit token at that point. And until this point, the 3 in, 3 out for 1 in rule applies. But next slide will show you the same thing that you saw before, but as the initial from the server reaches the client generates some new cryptographic keys to protect the handshake packets. That handshake packet is proof that the client saw the server keys. And so that allows us to proceed by layering in the address validation process without paying any extra bytes at all. I hope that's clear, but that's a trick that we apply in a couple of other places. Next, please. But of course, that goes both ways. The server needs to prove that it saw the client initial as well. So the client needs to confirm that the server is willing to talk to it. And at this point, we have a little trick. These initial keys that I told you have a version specific thing are actually derived based on what we use, what we call a connection ID. And that connection ID is an unguessable value from the client. And so when the server responds using that connection ID or using keys derived from that connection ID, then the client can confirm that the server is willing to talk to it. So not only does the server proven that it understands the version of QUIC that's being involved, it's also proving that it's willing to talk to the client by responding to it in this way. And that retry thing that we talked about before, we need to have the same sort of mechanism there. That has a different mechanism for managing that same process, but there's an integrity check in there as well. Next. So that's the implicit token that we have on the server side. Next. Okay, yeah, so all of this is somewhat fiddly to get right. There were a lot of deadlocks that we discovered in the process. I think we spent, the better part of 2 years going back and forth over some of the more tricky ones. Certain people had a very good habit of finding new ones every time we thought we fixed them. One thing that is still a little point of discomfort for some of us is that we don't really have any formal verification to support the correctness of the handshake. We've spoken to academics about this one, and there are systems out there that might be able to prove these sorts of things, but it's rather challenging. And I didn't even talk about version negotiation, which adds even more complexity, but I won't talk about that here because we don't have the time. Next, please. Brief on migration. The migration process follows the same 3 out for every 1 in rule. We have migration for a number of reasons. Probably the most interesting one is a client that is sitting behind a NAT and they get given an address and they happily talk to a server back and forth, and then they go quiet for a little while because, well, they just don't have anything to say at that point. And when they restart the communication after that brief period, the NAT has decided that it's going to give it a different IP address on that flow. And so what the server sees is a message from the client that has a new IP address that is completely unvalidated. And that could be maybe an attack. And so if it were to continue sending large amounts of data to that new address, bad things might happen because that might be spoofed. Of course, in a lot of cases, most cases, in fact, it's just the NATs doing what NATs do. Next, please. So we want to deal with NAT binding changes. We want to allow connections to move to new paths even, legitimately. But we also want to ensure that an attacker can't force someone to move if they don't want to move. We also want to ensure that an attacker can't stop someone from moving if they want to move. And unfortunately, if we were to show you an IP and UDP packet header, they're not protected, and the network rewrites them all the time. In fact, to some extent, we kind of rely on the network being able to rewrite these things. Maybe that was a bad idea, but that's the network that we have. And so we're in this kind of really awkward situation. So next slide, please. There we go. So migration looks like this. You have an established connection between client and server, and maybe an attacker takes one of your packets, maybe it's a packet that you had dropped, and sends it from a new address. The server looks at this packet and says, I'm not sure about this one. This might be legitimate. I don't know. And so what it does is probes that address, saying, here's a token. Prove to me that you're live on this address. But it also, and this took a long time to realize, it also sends a probe to the old address and says, prove to me that you're at this address. The client just responds to these probes as it sees them. If it's legitimately moving to the new address, then it will respond from the new address and proceed. If it's still on the old address and the attacker decided that it wanted to force the client to migrate to a new path, then the attacker should be unable to produce the correct response. And whichever one wins, whichever one's legitimate, will produce a response that the server will then respect, and valid migration will proceed. Next, please. So in order to get this to work, we didn't want to solve the problem that ICE solves, so only clients can migrate in this version of QUIC anyway. Servers can ask clients to migrate, but only once. We have this thing that happens during the handshake that allows it to happen, but clients are the ones that initiate the process. Migration is very simple at some levels. You simply detect that an address has changed on the other end and you start sending data to that address, but you only follow the 3 times rule until you've managed to validate that. And the validation process was on the previous slide. Next, please. And I think we're up. So having this very simple 3 times anti-amplification rule applies to all addresses. It's pretty straightforward to apply. You need to validate all paths before you speak on them. And simplifying to the client only means that we don't end up with complications in the protocol state machine where both sides decide to migrate at the same time, which doesn't really work very well. And then that leads into a whole set of other design problems where we use connection IDs on different paths, but I haven't spoken about connection IDs and probably shouldn't because I don't have time. Next. So that's only sort of a taste of all the security relevant things. We could probably spend another couple of hours talking about how packets are protected, how the packet header is protected, which was an interesting story there. Key rotation is a part of that. We also provide an equivalent to a TCP reset, which we call a stateless reset. That allows a server that loses state to clear up any connections that might be hanging around from before when it lost that state. That is secure. So TCP resets cannot be injected by the network. We also have a whole version negotiation thing that is nearing publication that requires a whole lot of interesting discussions as well, but not enough time to cover all those things here today. And that's me done. Thank you.
Thank you very much. So I think my favorite thing that I learned today, after having stared at QUIC for most of its development, is that nobody knows where that 3x rule came from, because I dug into it a little bit too. That was Ian. Ian did it. Thank you, Ian.
2 isn't big enough.
2 is not big enough,
Four
right?
is too many.
And 4 is too many.
Well, no, well, 4 might be okay, but
4's not
Great.
honestly, no one really knows. It was pulled out of the air, I think.
Yeah. And it seems right.
All right. Yeah. So Ian knows. Talk to Ian.
Ian knows. Talk to Ian. Ian
Talk
will
to Ian.
will talk about that tomorrow as to where that 3x is. Yeah. Oh, yeah, that makes a lot of sense. Cool. So thank you all very much for being with us so early this morning. Thanks especially to our speakers. Excellent presentations. We hope to see all of you and more tomorrow morning at 7:30, not at 8. We have a little bit of extra time for the panel discussion, and we ran early as opposed to running late on that one. So yes, thank you all very much and enjoy your IETF.